Hey everyone, and welcome to this explainer. Today we are diving deep into Chapter 20, focusing on performance engineering with observability. Most of us probably think of observability as just a reliability tool, right? Like a reactive alarm system that just helps us keep the lights on and fix whatever breaks. But what if we flip that script? What if observability wasn't just for firefighting, but was actually a proactive engine for radically speeding up your systems and slashing your infrastructure costs? We're going to explore exactly how maturing your observability practice lays the groundwork for a highly disciplined performance engineering culture. And to kick things off, let's look at a really compelling technical mystery that proves exactly why you need this mindset. All right, let's jump right into this mystery. Picture this, it's December 2021. The engineering team over at Honeycomb was digging into their systems when they found this bizarre discrepancy in their ingest service. Now, this is the endpoint responsible for taking in single wide event payloads. They're staring at their performance data, and something was just completely off. Time was literally going missing. The team was totally baffled, and this kicked off an investigation that would ultimately completely transform their approach to system optimization. So look at the stark conflict we have here. On one hand, the application server's auto-instrumentation spans were insisting that these ingest requests were lightning fast. We're talking taking only tenths of a millisecond to finish. But on the other hand, the load balancer logs were telling a completely different story. They were clocking those exact same requests at single-digit milliseconds. The load balancer basically proved that time was evaporating into thin air before the tracing hook inside the app ever even fired. And because that tracing hook was only called after the request was already matched to a route, tracing alone never would have caught this blind spot. And the fix for this silent latency culprit, which, by the way, was secretly dragging down performance for all their customers, was literally just 5 lines of code. Just 5. A deep dive showed that the HTTP router was actually being discarded and recreated after every single request, instead of just being reused as a singleton. By fixing those 5 little lines, they instantly clawed back all that missing time. But the really important thing here, this single event sparked a massive shift. It showed the whole engineering team the sheer potential of proactive system optimization, proving that massive gains are very often hiding right in plain sight. This specific fix perfectly highlights a broader discipline that we call performance engineering. And it's not just about slapping a quick patch on things when they run slow. It is the disciplined pursuit of making systems faster, more efficient, and way more cost-effective. It fundamentally shifts our mindset from just keeping the lights on, merely surviving from one pager alert to the next, to actively and meticulously perfecting the system. It's all about taking that exact same high-resolution data we already use for debugging and using it to systematically engineer a vastly superior architecture. Historically, performance engineers have kind of been stuck using completely disjointed, disparate tooling compared to operations or software engineering teams. We've all been trying to hit the same goal, but our siloed tools have forced us to look at completely different layers of the stack. So to get to an ideal state, we need a massive mindset shift. We absolutely have to bring these isolated disciplines together. We're talking about moving from reactive to proactive debugging and distributing that performance expertise across the entire team. By unifying our tooling, we empower every single engineer to own, interrogate, and optimize their code directly in production. Now, you might be wondering why dedicate so much time to this? Well, it's driven by 2 very tangible core business needs: lowering infrastructure costs to protect the bottom line and speeding up customer experiences to drive engagement. We aren't just hyper-optimizing some random function or writing inscrutable code just for academic fun. No, we're doing this to move the needle on real metrics that actually impact the company's survival. If your cloud bill is creeping up relative to your headcount, or if gross margins dictate whether your business is viable, then this discipline is absolutely essential. And here is the really cool part. You can achieve massive cost optimizations on the back end without even requiring developers to modify a single line of their app code. We all know getting performance work onto a busy product team's roadmap can be practically impossible, but you can tune serverless concurrency just by looking at the number of concurrent trace spans. You can use utilization metrics to know exactly when to shift a sustained workload over to a more efficient compute model, or maybe even when to retire a platform entirely. It is hands-off optimization, and it's powered entirely by your observability data. Looking directly at a resource utilization chart like this really helps visually ground that abstract idea of infrastructure waste. When you track total CPU and memory utilization right alongside the unused reservations of pods over, say, a week-long period, things get really clear. When you map additive measures like request cost directly onto your charts, you can pinpoint exactly when and where your compute resources are just sitting there completely idle. It totally takes the guesswork out of capacity planning, showing you exactly where your cloud budget is leaking out. But hey, sometimes the bottleneck isn't actually in your application code at all. And that is exactly where fleet-wide profiling becomes incredibly valuable. Think of it like casting a really wide net to catch inefficiencies that are hiding deep down in the operating system, the kernel, or shared libraries. If you can track down and solve a performance issue that impacts multiple workloads across your entire architecture, instead of just optimizing one single app, the compounding benefits of that are just absolutely incredible. Let's talk about the math of scale for a second. Saving a mere 1% of compute time on a single isolated task, that might seem completely trivial. Honestly, it might not even seem worth 10 minutes of an engineer's time. But when that 1% generalizes across your entire fleet of workloads, boom, that equals massive financial savings. Finding these tiny, fleet-wide inefficiencies through continuous profiling turns microscopic code tweaks into macroscopic budget reductions. Okay, let's pivot to this critical requirement, continuous telemetry. While it is super handy to catch a misbehaving service in a unit test or staging environment, the reality is that problems almost never happen in the real world while we're actually watching them. By the time your pager goes off, the anomaly might have already vanished. So our systems must scale out profile collection continuously. We need this telemetry constantly flowing in the background so we can interrogate it after the fact without ever needing to catch the system red-handed. I absolutely love this quote from the text because it calls out a trap we all fall into. As engineers, we love to just dive in and start prematurely optimizing SQL queries or trimming tight loops with early exits. But without observability acting as our magnifying glass to actually prove those areas have the biggest impact, it's essentially just educated guesswork. Sure, for a veteran engineer who knows a domain inside out, intuition works sometimes. But if we want to empower an entire engineering org, we need hard data. Otherwise, we risk wasting tons of valuable engineering cycles fixing the wrong problems. So, to eliminate that guesswork, we have to contrast and combine our tools. Tracing and profiling give us fundamentally different lenses. Tracing gives us that broad, request-level journey, the outer function context, right? It gives you an analytics and waterfall view so you can validate your hypotheses super quickly. Profiling, on the other hand, gives us the microscopic, inner function detail across the process. But to some degree, profiling usually requires you to already know which specific part of your system you even want to look at. And this brings us to an incredible realization from Chapter 20. What if you didn't have to choose between the broad context of tracing and the microscopic detail of profiling? The text tells us that when profiles are indexed down to the level of individual seconds of data, or even better, tied directly to individual trace spans, absolute magic happens. By blending these two signals together, we completely eliminate the blind spots you'd normally get from using either tool in isolation. Because by tying profiles directly to trace spans, you are instantly empowered. Think about it. You can simultaneously answer what was slow, for whom it was slow, why it happened, and exactly how it happened all at the same time without guessing. You have all the visibility after the fact to know exactly what's being called in a tight loop, and that lets you optimize in precisely the right places, backed up by a totally clear explanation of why you're doing it. And that magic combination is exactly what builds long-term success. Look, a lot of people fall for the myth of the 30% leap. This idea that performance engineering is about finding one massive silver bullet optimization on day one. But the reality is way different. True performance engineering is a scale with diminishing returns at the top, but huge gains early on that you have to continuously reinforce. It's really all about the compounding interest of tiny, continuous 0.5% to 2% improvements over time that slowly but surely transform your architecture. But remember, before you can optimize anything, you absolutely must establish your baselines. You've got to gather data on performance and cost well in advance of running any test. Why? Because this ensures you are actually working on the right part of your code base to have the biggest possible impact. It gives you the solid mathematical foundation you need to rigorously quantify the impact of your future changes, whether you're measuring latency, data size, dollars saved, or hey, even carbon emissions. Which brings us to the continuous core loop of this entire practice. It is beautifully simple, but it requires incredible discipline. Step 1, measure to find a potential improvement. Step 2, do the improvement. Step 3, measure the effects to prove it actually worked. And step 4, repeat. This isn't just a one-and-done weekend project. It is an actionable, repeatable framework that empowers your whole team to systematically ratchet down latency, boost the user experience, and lower those infrastructure costs day in and day out. So as we wrap up this explainer, I want to leave you with a really thought-provoking question. What silent bottlenecks are currently eating your cloud budget? Somewhere in your systems right now, maybe a router is getting discarded or a tight loop is just spinning uselessly. I challenge you to take this detective mindset and apply it to your own architecture. Bring your observability data to bear, empower your engineers, and go uncover that hidden waste in your infrastructure today. Thanks so much for joining this explainer, and keep optimizing.